Good day, ladies and gentlemen, and we are back again together, and we are still looking at that November 2018 paper from the IEB, and yeah, we're trying to help you prepare for that final exam, for those final exams, that is, and we're going to just make sure that throughout this week, as you prepare, we are there to assist. Okay, so if you haven't subscribed, please just be part of the family. Okay, just make sure that you add to our numbers. And by the way, we've been growing phenomenally. Thank you to all of you guys. Just make sure that you just keep inviting people and just tell them how much you are able to benefit from this channel. All right, so I'm going to start with question 5 from this paper, and this is based on a lot of it on kinematics, momentum and so on. And yeah, let's get right into it together. Right, so on question 5, they say students are performing an experiment in the lab. Okay, so we've got a 0.9 kilogram trolley that is traveling at a constant velocity of 2.4 meters per second. All right, you can see that trolley over there, okay, which is traveling in that direction at 2.4 meters per second. Okay, we know the mass is 0.9, and they said it's moving along a frictionless track. Okay, that's going to be very important if we're going to look at momentum, right? So they say when a metal cylinder has a mass m, okay, is dropped vertically onto the trolley. Okay, the trolley with the cylinder continues to move with the velocity v as shown in the diagram. Okay, so we're going to drop that mass m there, and there they are now moving together, but they're moving with a speed v. Now they say the student use the video analysis to plot the following position versus time graph on the trolley. All right, so there's our trolley, our position versus time graph. If you don't mind, I'm just going to move this so that we can see the rest of the questions. They say use the graph to determine the magnitude of the velocity of the trolley after the metal cylinder is dropped on the trolley. Now, before I just go into just answering the question, again, we just need to familiarize ourselves what actually does the position time graph actually tell us. Now, if you think about the gradient underneath this graph, okay, position is in meters and time is in seconds. If you think about it, normally when you calculate gradient, you're going to say change in y over change in x. So think about if we take the units, it's meters divided by seconds. Are you getting the picture? Meters divided by seconds, what does that give you? Meters per second, right? So in this case, it means that the gradient underneath this graph is going to be actually the velocity of the actual system, the trolley and the other mess afterwards. Now, if you think about it, at this point here, this must tell you that you can see the gradient is much steeper, meaning you are covering a higher position, or you are covering a higher distance, okay, within a particular time. But then after this here, you can see that gradient kind of becomes less. So it means you have a lesser velocity over this point here. And of course, it must be at that point where the other mass was added onto the trolley. Okay, of course, it's going to slow down in this case. So essentially, this is obviously the velocity before, and this must be the velocity afterwards. Okay, right. Now they said to us we should determine the magnitude of the velocity of the trolley after the metal cylinder is dropped. So at which point is that? It's between the second, okay, second number 2 to second number 5. So I'm just simply going to calculate the gradient over there. So my gradient, we're just simply going to say, well, m, in this case, we're going to say that's change in x divided by change in time. Okay. Right. So in this case, we're calculating our gradient. So what is our gradient? Let's find out over here. So we're going to say 10.2, but when the time was, when the position was 10.2, the time was 5, right? So I'm going to say 10.2. I'm going to subtract that velocity or over there, that position, 4.8 divided by, okay, let's calculate the time there. That's 5 minus subtract 2, right? And we get a velocity of okay, and I get a speed of 1.8 meters per second. Okay, so that's the velocity that we get. Okay, and remember we were answering question 5.1.1 there. Okay, please don't forget that. All right, so that's how we'll get our velocity. That's our velocity afterwards, right? And then they say to us, the law of conservation of momentum is a consequence of which Newton's laws? Right, so in answering that question, I would certainly go for Newton's second law. If you think about it, if a resultant force acts on a body, so if a collision takes place, there will be a force that is exerted on either one of the two, right? And either body is either going to accelerate in the direction of the resultant force, right? We say acceleration is directly proportional to the force and inversely proportional to the mass of the object. But I wouldn't fault anyone if they were also to go into Newton's third law. If you think about it, it says if body A exerts a force on body B, then body B will exert an equal but opposite force on body A, right? So in fact, to be quite honest with you, I'd accept any answer between the two because in a sense they are both somewhat applicable, right? So yeah, you can go for that in terms of those answers. So let's go to the next one. So 5.1.3, they say calculate the mass m of the cylinder. So what I'm simply going to do is I'm going to now apply the principle of conservation of linear momentum, right, on the trolley as well as that mass there. So I'm going to say, well, sum of momentum, okay, or you can say momentum before is equal to the sum of their momentas after collision, okay, after. All right, now remember we're talking about the momentum of the trolley, so I'm just going to show it there. Momentum of the trolley plus the momentum of the mass, I don't know what I'll call it, which is equal to, after collision, remember that both the trolley and the mass became sort of one system. So I'm just going to say momentum of trolley plus the momentum of the mass. Well, yeah, the trolley plus mass, right? So if you think about it, before collision, the trolley was moving on its own, right? Now, in this case, I want you to please listen carefully because I want you to get this. So the trolley, the momentum of the trolley, so we know that the mass was 0.9. Oh, just something to also just consider. Please remember, we always choose a positive direction when we have to go for the application of linear momentum. And the reason is very, very important because momentum is a vector quantity, right? So in this case, I'm choosing that direction to be positive. So it means that my velocity 2.4 should be a positive velocity. Now, let's talk about the momentum of that mass before collision. So this mass was moving vertically downwards, okay? So if it is moving vertically downwards, what is its horizontal velocity? Its horizontal velocity is 0. Think about it. What is velocity? Velocity is a change in position over time. So think about horizontally. As it's moving downwards, right? Is it changing position in the horizontal direction? And the answer is no. So in this case, in the horizontal, There is no change in position, so as a result it means that its horizontal velocity is 0, and thus the momentum will also be 0 horizontally. Okay, right, I hope that makes sense. So we won't regard the fact that it was descending. All right, so it was going down. So in this case, okay, after collision, so we know that the trolley and the mass were both together. So I'm going to say, well, it's going to be 0.9 plus mass m, but remember, both of them were moving with velocity v. Okay. In fact, let's just not waste time about it. Remember, we'd already found the velocity v when they were moving together. It's the one we calculated there. So I'm just going to just substitute it there as 1.8, and we found that to be positive as well, right? Now we can just do our mathematical gymnastics. So I'm going to just simply say, well, that's 0.9 multiplied by 2.4. Okay, so times 2.4. Okay, so I'm 2.4, and I get a value of 2.16, okay, for both of them. And in this case, I'm going to divide by 1.8, okay, so that I cancel on this side. Divide by 1.8, okay, and that's, I get 1.2, but I'm now going to subtract 0.9. Minus 0.9. You can do it however you want to do it, okay, but ultimately we should get to the same point, and I get a mass of 0.3 kilograms. Okay, so that mass there was 0.3 kilograms. Right, okay, we are moving swiftly. We found the mass. Now they say, why is the vertical velocity of the falling metal cylinder, I should have said the mass, the momentum of the cylinder there instead of the momentum of the mass. But yeah, I know you get my point, right? Okay, so they say, why was it not taken into consideration? Okay, now I think I'd already explained this part. Why did we not consider the mass of the cylinder? Well, the reason is that, remember, the cylinder is actually moving vertically. So what is its change in position in the horizontal direction? Okay, there is absolutely no change in position. So as a result, that metal cylinder is actually moving at 0 velocity horizontally. Okay, so I hope you will obviously write that down in a way that you understand. All right, let's move on to the next question. We go to the next page. All right, moving along, they say a steel hammer with a mass of 600 kilograms is used to drive an iron beam into the ground. Okay, so there's our steel hammer there, and there's our iron beam. Okay, they say the steel hammer falls a distance of 3.5 meters from rest under gravity before contacting the beam. The beam is driven a distance of 16 centimeters into the ground before coming to rest. They say ignore air resistance. All right, so in this case, this tells us that this is a falling body. This is a falling object, or in this case, it's vertical projectile motion. Okay, because there is no air resistance in that case, so it means that gravity is the only force that acts on the steel hammer. Right, now they say to us, state the principle of conservation of mechanical energy. And just a hint, whenever they ask for that principle, there's a very great chance that you might have to use it in the next question. Okay, so let's have a look at you remember that principle. In an isolated system, the total mechanical energy remains constant. Okay, right, so let's go for the next one. They say calculate the magnitude of the velocity of the steel hammer as it strikes the iron beam. So we want to know, what was the speed of the steel hammer at this point here. So if we are to think about it, so all right, let's just have a slight discussion about it. So in this case, I'm going to just take just a small little drawing. So this is the point where it started from. This is the point where it collided with the beam. Okay, so I know that the velocity at this point here is 0, right? So it started with a velocity of 0, but just before hitting the ion beam, in this case, we want to find out what is the speed at this point here. So what I'm going to do, because they've kind of given us a hint there, I'm going to use principles of mechanical energy. Why? Because there is no applied force and there's no frictional force, and it tells me this is an isolated system. So I'm going to say, let's call this point here, let's call it point A, let's call that point B. So I'm going to say, well, EMEC, or you can say mechanical energy at point A is equal to EMEC at point B. So I know mechanical energy at point A, which is when it left that point there, will be the same as the mechanical energy when it gets to the bottom there. Right, so it falls a distance of 3.5 meters. Okay, so I am going to simply say, all right, so mechanical energy at A, all right, I'm just going to take that, if you don't mind, I'm going to take that point here as my 0 position, the top there. I'm going to take this as my 0 position, meaning that I'm going to consider the potential energy at this point as 0, right, and that height there will be 3.5. So I'm going to say, but what is the mechanical energy? Mechanical energy is the sum of kinetic and potential energy at A, right? It's equal to the sum of kinetic and potential energy at position B. Now let's talk. So is the kinetic energy at A? Well, remember that our initial velocity was 0, so it means that our kinetic energy would be 0 at that point there. But what about potential energy? Definitely there is, because we're at a height of 3.5 there. So I'm going to say this is mgh at A, okay? And then when you look at kinetic energy, at this point we want the velocity, so it must mean that it had a significant kinetic energy over there. So this is half mvb squared, right? But remember I said I'm considering that as my 0 potential point. So in this case it means that my potential energy will be regarded as 0, okay? Right. By the way, the beauty about this is that even if they didn't give me the mass of the steel hammer, in this case, I can just simply divide both sides by the mass, okay? And that gets rid of those two. So I know my gravitational acceleration, that's 9.8 multiplied by the height was 3.5, okay? And this is equal to 1 over 2 times VB squared. Of course, we can multiply both sides by 2 to get rid of that half there. Okay, so multiply by 2 there, but what I do on the right, I do on the left. So that will be 2 times 9.8 times 3.5, and we take the square root there, and a square root of the answer, I get a value of VB is 8.28. Okay, please, you can verify it, and just please find out if I'm still on the right track. All right, so that's our velocity when it got to that point there, just as it hit the steel, the iron beam, right? Okay, let's go to the next one. By the way, just another point there, you could have actually used equations of motion here. They were not really specific which principle to use. If they had said use principles of energy, of course we would have been subjected to this, but we could have as well used equations of motion. Think about it. Your initial velocity is 0, your final velocity is unknown, that's what you're looking for. You've got the distance, but you also have gravitational acceleration. Remember that it was moving due to gravity. Okay, right. I'm just going to move this over to this side. Okay, just keep in mind that speed there is 8.28. Right, now they then say to us, we're looking for now, they said state the work energy theorem. Okay, remember the work energy theorem just simply says that the net work done on an object is equal to the change in kinetic energy. Okay, by the way, you should be able to by now just state those. Okay, right, now they say calculate the magnitude of the average net force the beam exerts on the hammer while the hammer is brought to rest on the beam. All right, now I want you to think about it. Okay, so the beam or rather the hammer landed on the beam and it drove it down 16 centimeters. Okay, so if you think about it, if the iron beam went down 16 centimeters, so that happened as well on the hammer, right? As it hit the beam, it was also driven down at 16 centimeters. I want you to think about it. So you hit something there, all right? So there it is. There's your, I'm terrible at drawing, right? So there's a hammer hitting the beam. If the beam goes down 16 centimeters, the hammer also goes down 16 centimeters. So if you think about the hammer between those 2 points, so what happens is that it arrived here with a speed that we calculated of 8.28 meters per second, okay, and was immediately stopped at this point here. So it was stopped. So it started at 8.28. It stopped at this point here, after driving this guy down. And what was the distance at which it was stopped? And by the way, just to remind you, ladies and gents, it simply means that at this point when it was in contact with the beam, it could not have been moving now due to gravity only. Okay, so you cannot use vertical projectile motion principles there, because gravity is not the only force that is acting, right? So it was driven down 16 centimeters. That's the distance there. So we were looking, by the way, they said calculate the magnitude of the average net force. Okay. Now there are 2 ways in which I can approach this. In fact, you know what, for the sake, because we're doing revision, let's just go for both of them. So I can actually find out the acceleration there, right? So I can say, well, the net work done, okay, in fact, I wanted to talk about the F net rather, but now that I've talked about the net work done, we might as well just go for it, right? Okay, so I'll say, well, the net work done, okay, will be equal to the change in kinetic energy. So that's the first approach I can take, right? But what is net work done? I can say, well, but net work done is F net multiplied by delta x, the cos of angle theta, okay? And this would be equals to EK final, kinetic energy final, minus kinetic energy initial. So remember, the final kinetic energy is this one here, and our initial, this is the final velocity, this is the initial velocity. Now, we're looking for the net force, isn't it? So I'll say, well, it means that F net, right, multiplied by what is our displacement? They said 16 centimeters, and remember, we need to convert that into meters, right? So it means we'll just simply say 16 divided by 1,000, and that will give us 0.16. That's our displacement. Okay, now I want you to think about it. As the steel beam is going down, it's decelerating. Okay, so it means that our net force is actually pointing upwards. Direction of motion is down. Frictional force is actually up, not frictional force, rather, the force that the beam exerts on the hammer, okay, is a force upwards, and that's why it slows down until it gets to zero. So it means that it's accelerating in the opposite direction. So as a result, it means that direction of motion is downwards, and force in question, which is the net force, is actually upwards. So as a result, I will say, well, this is going to be the cos of 180. Okay. For those of you who may not understand this, please, it means that you haven't watched our video on work, energy, and power. Please just go there, and guys, I would actually recommend binge on those videos. They will really help you a lot. Right, so kinetic energy final, okay, remember it's 0 here, minus kinetic energy. So my kinetic energy, my velocity is 0 there, and so my kinetic energy will be based, will also be 0. So that will be half. The mass of the hammer is 600, okay, and the velocity or the speed of the hammer before was 8.28 squared. All right, so let's try and find that net force there. So let's find out what we have on the left hand side. So it means we'll say minus a half, okay, times 600 multiplied by 8.28 squared, and I get a value minus 20 point, that value there. And I'm going to now divide that because I want F net. So I'm going to divide that by 0.16, the cos of 180, and remember cos of 180 is -1. So it means I am dividing by -0.16, and I get a value of, so the net force is going to be 128,547 newtons. Okay, so that's the force that I get there. So another way that you could have tackled this is that you could have used equations of motion, right? And said, look, we can find out what the acceleration is. And so I would find the acceleration by simply saying, right, so let's find the relevant equation. I would say, well, Vf squared, or you can say V squared is equals to U squared plus 2as. Okay, so what is my final velocity? That was 0. My initial velocity was 8.28 squared, okay, plus 2 times, I'm looking for that A, and my displacement was 0.16. That is if I took down as positive, right? You would get that acceleration there, and after finding the acceleration, you would now say F net is equal to ma, right? You'd use the mass, which is 600, and the acceleration that you would have got in there, and I'm sure you'll end up at the same position, right? You can try it and see if you do get the same answer. All right, so the next question, okay, they say to us, the machine that is used to raise the hammer, okay, they say is used to raise the hammer so that it can be used again, has a power output of 180 watts. So I'm going to have to make an assumption there, okay? I wish that the examiner could have actually been more specific on this question, but nonetheless, it is what it is, okay? So I'm going to have to make an assumption that they're using this machine, and in lifting the hammer, it's actually going to be moving at a constant speed. Okay, so I'll tell you why that is relevant, because in lifting the hammer, there are two things that can happen. You can change potential energy, which of course we will here, but you can also be accelerating, it could be accelerating lifting it at a changing velocity. But in this case, what I'm going to do is I'm going to have to assume that it was lifting this hammer with a constant velocity. It means that there was no change in kinetic energy. So the work that would be done here would be the work done to change potential energy. So I will say, well, to answer that question 5.2.5, okay, I'll say, well, the potential energy is equal to mass times gravity times height. So that will be 600 times 9.8 multiplied by the vertical height in which it was raised was 3.5. Okay, and in this case I find that the potential energy, that's 600 times 9.8 times 3.5. okay, and I get a value of 20,580. okay, 20,580 joules. Remember, that's energy, right? So I will say, well, but what is power? Power is the rate at which work is done. Okay, so this is work done divided by the change in time. In this case, I've got the power. It's 180 watts. I was given the power there. So I know that I'm looking for the time. So I can just make time the subject of my formula, or you can just substitute there. I know power is 180. I know work done. It's the work done to change potential energy. So I've got 20,580. Okay, divide that by time. And you can just simply do your mathematical gymnastics there. Okay, so that means that we're going to cross multiply and divide by 180. So I'm going to take that value that we had, 580, and I'm going to divide it by 180, and I get a time of 114.33 seconds. Okay, so means that the time taken would be 114. Of course, you can just verify for me, ladies and gents. Okay, so if you wanted to convert that to minutes, since they didn't specify, so you can divide that by 60, and I get 1.9 of a minute. Okay, yeah, I'm not going to dwell too much onto that. Right, so that is what we get in terms of seconds. All right, and yeah, we would have gotten ourselves that 27 marks, and I hope it's been really worth it and you understood that question. All right, and I'll see you guys again next time. Sharp.